In the next example, we will have to interpret part of the question from the picture here. So we have a spring. Here's the spring's natural length with no weight on it. And then putting this weight on it, and this is equilibrium, it's not moving at all. It stretches at 2 feet. So, if beta, remember what beta is? That's the damping constant, is at 2. And the initial position of the mass is at equilibrium, but the velocity at time 0 is -3, which means there's an upward push making the velocity -3 feet per second in that direction. We need to find x of t. So we'll write the differential equation and solve it. Well, here's the differential equation. I made a few notes here already. Notice that force is equal to Ks. S is the distance that this stretches the spring to the equilibrium. So this is at this right here. S is 2. We're looking for the spring constant. The force is 8 pounds. So that means 8 is equal to 2K, or K is equal to 4 pounds per foot. That's the spring constant. And then we need the mass, not the weight. We don't put 8 here. The force of weight is mass times gravity. 8 is equal to m times, remember that's 32 feet per second squared. And we get m, the mass is 1/4, and the units of that would be a slug, 1/4 slug. So that means that we can write this out. M is 1/4 d squared x dt squared plus beta, which is given to us to be 2 dx dt, plus kx, and we computed k to be 4, is equal to 0. And I'm going to come way back here. That implies, let's get rid of this. So we have a 1 as a coefficient of that first second derivative term. Multiply everything by 4. Then we'll get d squared x dt squared plus 8 dx dt plus 16x equals 0. Now let's just do a test real quickly. Remember that 8 is equal to 2 lambda, and this is omega squared, those coefficients. So if we wanted to know what capital D was, the discriminant, so we'll know which case we have. If we have 2 distinct roots, 1 repeated real root, or 2 complex roots. This was lambda squared minus omega squared, which means, let's see, 2 lambda is 8, so lambda is 4. So capital D is 4 squared minus, and this was omega squared, 16. Okay, so the discriminant is going to be 0. We're going to find that out already, but we're just proving again that the theorem does work. Okay, so characteristic equation, m squared plus 8m plus 16 equals 0. M plus 4 quantity squared equals 0. So we have m equal to -4. I'll even write it twice just to show that we got 1 repeated root. And that tells us the generic solution, the general solution, x of t is equal to c1 plus c2t e to the -4t. Remember that? Okay, let's go ahead and figure out the C1 and C2 based upon our initial values that were given to us. So we have Well, let me write out x of t here, and I'm going to multiply it through so I get c1 e to the negative 4t plus c2t e to the negative 4t, so that I can write out right underneath it the derivative, which we'll need. And the derivative is negative 4 c1 e to the negative 4t plus c2 t times negative 4 times e to the negative 4t. And the last term is plus c2 e to the negative 4t. Okay, so when we plug in the initial conditions, let's use this one first. X is 0 when t is 0. So 0 is equal to c1 plus c2, nope, t is 0. So that was easy. c1 is just equal to 0. And then the next one says that at time 0, the derivative, x prime is 0 when, I'm sorry, x prime is negative 3 when t is 0. So now we're using this equation. And now we need to make t a 0. If t were a 0, we get negative 4c1. This t would make that term go away because t is 0, plus c2. Well, c1 is a 0, so c2 is equal to negative 3. So that gives us the solution very simply is x of t, it only has one term in it, negative 3t e to the negative 4t, negative 3t e to the negative 4t. Coming from this term. Okay, one more thing is we learned from the capital D being 0, or the fact that we had 2 repeated roots, that means it's critically damped. And so maybe I'll write that up here just to make a note. Critically damped. That's usually the most desirable case because we had 2 repeated roots in the characteristic equation. And just for information, I'm going to change color. If we were to graph this, what's happening is we're in positive territory here, but it's going to go up into negative territory and then never cross the equilibrium point again. So here's what the graph looks like. This is that's 0, that's position 0. That'd be this right here, equilibrium. And this point right here, if you set the derivative equal to 0 and solve it, you'll find out that it's negative 0.276. So maybe I should have scrunched that down quite a bit. So it barely would have gone, it was negative, it peaked, it just barely went past it, and then it just barely went up and then came and almost never, and it will never hit this again. That's the negative direction. This point right here is, let me write it as a decimal, it's 1/4, 0.25. Comma, negative 0.276. That happens to be its peak. in the negative direction. So one more time, it just barely goes above equilibrium and then never comes back down. You could picture that as being in such a viscous liquid that it just hardly moves. It's never going to get back to its equilibrium position.